Hello, this is Mr. Collier, and today we're doing definite integrals. Okay, so we'll just take a look at the concept of it. Like if you want to find the area under this curve, you can create a bunch of equal width rectangles, and you can easily get the area. The height is equal to like the y value of the function, and we go up in a certain step value. Anyway, you can put it into a bunch of rectangles. And use a computer, it's really easy to calculate this really quickly, the area of all those rectangles, right? Now, if you use these rectangles here, you have an underestimate because you're forgetting about, you're not using these little areas right here, right? So it's not going to be perfect, but it's going to be fairly close. If you use these rectangles, your area is going to be too big, okay? So you want to try to get something in between, or you want to make your rectangles smaller, okay? So the smaller you get, the closer your rectangle area is to the actual area. Here you have an underestimate over here, and here you have an overestimate. So you could do something like find the average of those. Or you can just make your rectangles smaller and smaller and smaller. And of course, a computer can do this in no time. So you can make the rectangle widths really, really tiny using technology and get an area that's really, really close. Okay, so that's the concept. Now your what a integral does, okay, this is the integral notation, is it actually calculates the exact area under a curve by doing technically a bunch of infinitely small rectangles. So basically just a bunch of lines, if you will, rectangles of zero width, and add them all together. That's what integral calculus does. Okay, so we have, now we'll do some of this stuff by hand later, but right now we're just going to use our calculator. You have an integral button, and you can find areas under curves using it. Okay, you got this thing here. Some people say this represents like an S for a sum, because you're adding up a bunch of infinite rectangles. But basically, the bottom one is the starting point, or starting X, we'll call it. And this is the final X, or whatever. This is where you stop, basically. Okay, so I should probably use the actual terms. This is the lower limit of integration. And the other one is the upper limit of integration. Okay, so how do we write this area? We can say the area is the integral from 0 to 2, because that's the starting value, 0, and then we go up to 2, and it's x squared plus 1 and dx. Dx is sort of like the decimal, or the period or the question mark at the end of a sentence. It's just part of the notation. Well, it does have a meaning, but we can think of it as just this is the beginning and this is the end. So this shows you where the integral stops, basically, right? Okay, so if you do this integral on your calculus, it gives you the exact area under the curve. Okay, so let's do that. Alright, so let's go to apps. Actually, we don't need to go to apps. We can click right here, this symbol button here, and click here. And this is 0 in the lower limit of integration, and 2, and x squared plus 1. And you gotta stick in the dx at the end. So that's 4.66. Or if you round it, that rounds it to 7. Or you might notice that's exactly 4 2/3. Okay? But you can also round to 3 significant figures on IB tests. Write down the definite integral that gives the area here. Okay, that's starting with 1, and then 4, and then the function equation is given, negative x plus 6 dx. Okay, so going to type that into the calculator. You can also notice it's a trapezium, so let's do it that way too and see if they match. The length of this side is 5, and this is 2, and the height is 3. So that's basically 21 divided by 2 is 10.5. And on your calculator, I think I have that here somewhere. Yes, the integral of negative x plus 6 is indeed 10.5. Okay, let's look at the next one. State the lower and upper limits of integration. The lower one is negative 1, and the upper one is 3. To graph it, that's linear. It's x plus 4. So this equation, this line's going, has a slope of 1, so it's going up this way. So that's what the equation looks like, or the line looks like. Use the GDC to determine the definite integral. Shade the regions. It was, negative 1 to 3. So negative 1 to 3 means we go from negative 1 to 3. Okay, so we're going to find the area. This makes with the x-axis. So that integral is negative 1 to 3. And just type in the function and a dx at the end. And that equals, let's see, I think I have that one done as well. Where is that? Here's 20. Okay, we can do it with the trapezoid formula. This is 3, and this one here is 7. The height is from negative 1 to 4 is 4. So that is indeed 20. Okay. Now you could do the same things, but with these functions here, but it is useful to look at the picture, because like if you got some section underneath, that's going to give you a negative area, so you might have to be careful, and you should check out the picture. Anyway, let's check it out. So let's type this one in. I get x cubed minus x plus 1. Okay, so that's cubic. And from negative 1 to 2, everything's above the x-axis, so yeah, we can just write down this interval. Okay, I just checked what it looked like here. By the way, if there's like a graph like, well, we're going to see that in a second, never mind. So I think I have this already worked out here somewhere. Here, it's 5.25. This graph is going to be a little bit more interesting. Let's check it out. Okay. So let's plot it. So this one, yeah, it's got a vertical asymptote at x equals 3. So let's check it out. Let's sketch that. So it looks like that. It's all above the x-axis, but x equals 0. So there's a vertical asymptote there, so you can't really work out the area here. So watch out for those kind of things. But we're going from positive 1 to positive 3. So we're talking about the area of this section. Okay, so the integral from 1 to 3, 1 over x squared plus 1, dx equals, and I think I have that one already done as well. That is 2.67 approximately. But you might notice that is exactly 2 3/3, but we can leave it like that if necessary. Here is in this next one, so we're going to find the integral, but we need to actually find these points first. These x-intercepts, you can get it pretty easily by setting that equal to 0, but Let's practice doing it with the calculator. We have negative x plus 1, and then we have x minus 3. Plot, don't need a multiplication sign maybe. Okay, so then we can find the roots. Actually, it looks like it's negative 1 and 3. Let's see. Yes, negative 1 and 3. So that means we do the integral from negative 1 to 3. It's just the x-intercepts. Okay, so we do that, and yeah, let's do that. So we just do it here. All right, do I already have it done? I already have it done right here. It's 10.7, or it's exactly 10 2/3 if you wish.